Hello, everyone. We're about to have a kickoff for the 2020 FRC season, and some people that before kickoff, I wanted to share these topics with them, so I titled this class "What to Do Before Kickoff." If you and the reason for going through this is to ensure that you've spent time mastering the LabVIEW skill set before you try to do any of the programming. And so I had a couple pages here of guidelines. First of all, resist the impulse to copy and paste, even though it's possible. And after you get good at it, it'll be a feature that you can use. But in the beginning, when you're first doing the LabVIEW programming, you'll find that you can actually propagate mistakes that you didn't intend. So try to resist copy and paste, at least on the front end. I like to emphasize not to let anyone put code in your program that you don't understand. That includes me. The point being that you'll have to debug the code at some point in time. So if you don't understand it, don't let the code be put in your program. I like to emphasize virtually every year I get resistance from students that don't want to use a mouse. Any professional CAD person, CAD in any vocation, uses a mouse. And so it's a good skill to pick up. In LabVIEW particularly, there are different capabilities based upon which mouse button you use that aren't available on your touchpad. So again, I like to encourage you to use the mouse whenever possible. Most of what I'm going to be covering are in the YouTube channel, so by all means, check that out when you get a chance. All LabVIEW programs are called VIs. Each VI has two windows: the front panel, which will have, have the controls, the indicators, and this will primarily be used in just these practice sessions, because when we get into the robot, we won't be using the front panel much. The second window is called a block diagram, and that's where all the code that is written and the functions are generated. And again, each button on the mouse will have different capabilities, so it's worth understanding to start off. On the block diagram, the inputs, I refer to the nipple on the left of each icon, and the output is on the right side of the icon. The program flow is from left to right. And I encourage people to use context help, especially in the front end of things. And so you can replay the video at your own speed and kind of review all this stuff rather than me go through and read it. For this particular session, I'm going to be using the blank VI, and the reason is that these will be programs that you can run on the computer without a robot. The next session, we will be focusing on the simulator, and therein you'll actually have a robot program that you can modify and understand what the impact is to the simulation, the robot that's simulated. The other thing I want you to do is, after you've built the program up and it's working properly, then play with the variables and see what changes can be made without disturbing the flow of the program. So it's your chance to break things so that you don't necessarily repeat those mistakes when we start to program the robot. All right, so we're going to start with a blank VI. This is the way the LabVIEW screen looks, the getting started window. And this particular year, even though it's the tail end of it, is good through the end of January for the code. Just a side note, before you install next generation LabVIEW, you need to uninstall this version. So be prepared to do that at kickoff. Okay, we're going to start with a blank VI. And First thing I want to do is basically having comparisons that utilize both analog and digital signals. So we're going to put an analog. I'm going to right click and under the numeric palette, pick up a knob, and right click under the numeric palette, pick up a meter. Likewise, I want to right click and pick up a push button, or let's go ahead and do a toggle switch from a Boolean palette. Let's have a Boolean indicator, rectangular LED shape. You'll notice as you move the cursor around, the icon on the screen has a different shape. When there's a dual-ended arrow, you can left click and drag and make the element larger. If there's a single-ended arrow, you can move that element around the screen. If there's a white knuckle, you can change the value that that indicator is showing. And this applies to all the different elements. We also want to put a meter here. Now what I want to do is make a comparison and have the computer do a function based upon exceeding a certain value. So in this particular case, here's my meter, here's my Boolean indicator, and here's my second meter. And what I want it to do is tell me when this signal gets above a certain value. I do that with a comparison palette. If I right click on the block diagram, I can open up all the functions palettes, and I want to look at the comparison palette and say when it's greater than or equal to a certain value to do something. So what we're going to do is when this value coming from a knob, I left click and connect it to the top of my comparator, and I want it to tell me when that value is exceeding 5.1, the value of 5.1 volts. If I hover over the left-hand nipple and right-click, I can create a constant, and we're going to make this 5.1. And the output, I want to be a Boolean. So you'll notice if I go to context help, if I go up to help, left click and show context help, when I hover over this element, it describes to me the function that it is performing. And so the top value is compared to the bottom value, and then we're given a Boolean signal that's true if the value is greater than the lower value. I'm going to right click and create a indicator. And as I go back to the front palette, the front panel, now this label is assigned to that LED. And I can see that here. There's my value that indicates X greater than Y. All right. Now also I want to control on my Boolean palette. If I right click on the block diagram, go to the comparison palette, there's a selector switch. And this gives me the ability to control signals at the output with this input of a Boolean value. So Boolean is a digital, and my two outputs, when the Boolean signal is false, I want to have 0 displayed on the meter. When the input is true, when the Boolean input is true, I want to create a constant that shows 6.7. Now, just like before, we want these to be repeated functions. So I'm going to right click, pick up the while loop, left click and drag to connect everything. Down here, I'm going to right click and create a constant. This way the loop will run indefinitely or infinitely long. I want to put it from the timing palette, which is the little time over here. I want to put a wristwatch, which will delay, and I'm going to put in right click and create a constant of 100 milliseconds. So it's going to change or run this program every 100 milliseconds. Okay, so now what I want it to do is to run, and I want, when this exceeds 5.1, I want to see that this light goes on. And sure enough, as I control this, at 5.0, the light goes off, and at 5.3, 5.2, anything above 5.10, it comes on. So this is the way signals are compared, and we digitize a signal. Now, if I come down here and flip the switch on, when the switch is true, when the variable is true, why did my second? Oh, I didn't see what my Boolean indicator was connected to. It's connected to the output from a switch. So when the Boolean is false, the output to the meter is 0. When the Boolean is true, the output to the meter is 6.1. All right. So again, this is just an example that you need to draw a couple times using various values and make sure it works okay for you. I'm going to go back and start a new blank one-line diagram. This time I want to have a gated signal. So a gated signal, again, we're going to have a knob here and a meter on the right. These both come from the numeric palette. I'm going to have a push button, rocker arm, a rocker button here, and I want to have my LED indicator here. Let's go expand it just to make it look different. All right, so the idea is I want to have a Boolean control of, this is a case structure, and have two different values come out of the case structure based upon the value that's being requested. So, and we're going to use a case structure to do that. So we right-click, go to the programming palette, pick up a case structure, which is the one with the little question mark on the left-hand side. It's got two cases, the true case and the false case. The control for this element, for this case structure, is going to be the Boolean signal. And when this is true, I want the value of the knob to be passed through to the meter. When this is false, I want the meter to indicate a constant number, which in this case will be 1.1. And this kind of control actually is required a lot in a robot, and it's gating the value of the knob with the Boolean signal. So when the Boolean is on, the knob's value will override or will be passed through. When the Boolean is false, then it only leaves us with a constant output from the case structure. We're going to do a while loop, create a constant, put in a time delay. This time I'm going to use 55 milliseconds. And it doesn't matter, at least for these examples, it doesn't matter what that value is. So it's worth playing around just to see what effect it has on response. We're going to run the program, and you can see there's a constant value. In this case, it looks like it's a 1 or something similar to 1, and there's no response when I move the knob. But when I turn my Boolean signal on, which opens up that gate, then the output follows the knob. So we're gating the analog signal with the Boolean signal. This could be a safety switch. This could be a limit switch that says we are aiming the wrong direction. It could be something else that says we're too close, but basically it's a go, no-go signal, and we're gating the analog output. Very useful function, and it's used all the time in robotic control systems. Okay, there's two basic types of computation in a robot. First of all, there's regular numerics. So I'm going to have two numeric controls, right click, and I want to build a 4-function calculator. If I right click and I go to the numeric palette, the 4 functions I want to simulate are addition, subtraction, multiplication, and division. Now, obviously, I can do more than that, but that's what we're going to focus on now. If I want this to look neat, I left-click and select these, and I go up to my tab up here that aligns objects, and I'm going to align to the left side. Now, each of these functions has 2 inputs, and so this is frankly a technique on how to do this type of construction. I want the first numeric number 1 to be connected to the upper input to each of the functions, and I want the bottom input to be connected to numeric number 2. And so there's multiple ways to do this, but the neater you are, the better off the code will look, and it'll be easier to follow by somebody else. Now, in this case, rather than create the outputs as an indicator, I'm going to do it from the block diagram. And the advantage here, and when I right-click, create an indicator, it's going to label what the function is. So that's a plus, an addition, right-click, create an indicator, subtraction, right-click, create an indicator. Now, if you recall, one of these functions is going to be undefined when we have division by 0. So part of this exercise is to recognize what the computer is going to do when that's the case, and that's what I want you to see. So create a constant here for my timing. And let's do this at 20 milliseconds, which is not necessary for human updates. Now again, another chance to make these neat. So I'm going to pull this down, left click and drag, align to the left side, and run the program. Okay, so in numeric value, 0 plus 0 is 0, 0 minus 0 is 0, 0 times 0, but any number divided by 0 is not a number, so nan is what the indicator shows. If we increase this value on numeric 1, we have 6, 6, and 0 because we have multiplication by 0, and we still have an infinite now because we have division by 0 is an infinite number. As soon as we make that a real number, now we start to get real number answers and things start to make sense. So this is a 4-function calculator. Now the other thing I want to kind of impress upon you is the value of labeling your code, both on, since we won't be using the front panel, it's less important there, but it's a good thing to do on the block diagram. All right, so that's a 4-function calculator with the numeric processes, and we're not going to save it. The second numeric system is actually the Boolean Algebra, and we're going to start off with 2 push buttons. And we're going to set them here with the 5 functions. So we're going to right click. I'm going to open up the Boolean palette. We want the AND function, the OR function, the invert function, exclusive OR, which is here, and I guess that works. We're not going to get into these other. Let's just make it 4 functions. We're going to do the same thing. All but one of these have 2 inputs. So we're going to make them neat. Now things make a difference here as to which order we do. So we can't really allow the, I can't swap out the bottom and top inputs. All right, so the second input I want to have here. Now, part of this exercise is to be able to recognize what the function does, because again, it's useful in doing a design. We're going to create indicators on the output, take advantage of the label. And put this in a while loop. And put a time limit on it, or time delay on it. Let's make this 50 milliseconds. Again, this is good practice, and it's the kind of thing you want to be able to do without having to follow the notes, because you want the construction to be second nature. You don't want to sit there and have to think about it. All right, so let's run it. Okay, so X and Y is false when both of these are not true. X or Y is false when neither are true, and not X is an inversion, so it inverts the signal. If it's the signal input is false, the signal output is true. So let's make Boolean 1 true. X and Y is still false because it's we only have one true. X or Y is true because we do have X true. X is inverted, so X not is false. And the X exclusive OR is true because we only have one of the elements that's true. If we put the second element true, we still have X and Y true. X or Y is true. X is still inverted to be false. And because this is an exclusive OR, it's only true when one or the other is true, and it's false when they're both true and when they're both false. Something to play with, and extremely valuable in design. If you got questions, by all means, feel free to email me, and we'll get into the details. Okay, a couple other things I wanted to cover. Yeah, I want to talk about nested loops, and so this is probably easiest if we just do a couple examples. But what it amounts to is we may have multiple settings, or the computer making a decision based upon, say, several different inputs, in this case 3. And what we want to have the output be is, let's have it a numeric value. And so we're going to do this with nested loops. We always nest case structures in the negative or false case. So it's going to take 3, and so each of these is going to be controlled by one of my Boolean signals. So in my false case, I'm going to draw another case structure. And again, this is an extremely valuable construction and use it almost every design that I do. All right, so again, this input controls the output, the outside case. This input controls the middle case. This input controls the inside case. And when all three are false, I want my output to be 0. So I'm going to right-click, create a constant, and then drag it to the center of my case structure. And it connects it up. Now, when the bottom signal is true, I want this to display a constant 1. When my middle signal is true, I want the display or the meter to display a constant. Let's try that again. Create a constant 4.5. And this is virtually always used in limits as well, if we don't want to exceed a certain limit on an increment stage. And so when the top signal is true, we want this to be 6.6. All right, I'm going to put everything in a while loop. Create a constant. Put in a delay. And set the delay for 20 milliseconds. Now it's worth playing with the time delay to see if it changes how quickly the program responds to my limit switches. Okay, when I have false across the board, my output is 0. If I have true on the top one, I get 6.1. True on the middle one, I get 4 something. And true on the bottom one, I get 1 something. Now, the advantage of a case structure over the select function, which we could do the same thing with that, is that this gives us the ability to have multiple signals. So for instance, let's come back here and create a numeric indicator. Now, this is an obvious, yeah. Let's do this over. So now, when I come back to my inside case, I can create a constant here. And it can be different from the values on the other signal. So let's say there is a 1. When this is a true, we'll create a constant 2.2. When this is true, we'll create, now these don't have to be any particular order. And when this is true, and very frequently these will be speeds that get delivered to certain motors in the robot. So again, we run the program. When this is true, we get numbers on our outputs. Now there's also a built-in effect where each switch, the outside switch takes priority over the other two because it's daisy chained the way it is. So the Boolean 1 is the only output that shows up if it's on, whereas if it's not on, then the other two will not be overridden. Okay, so that's called nested loops, and it's worth playing with. And again, I invite you to kind of go through the video at your own rate and see if you can duplicate the outputs that I did. Okay, so the next class is going to be all about the simulator. And probably one of the most important tools that an engineer has in his tool belt is either a prototype or a simulator. A prototype allows us to build a physical structure that's similar to what we want to build and allows us to work through the problems which could be encountered trying to build that particular structure. The simulator, on the other hand, is a pre-built object that lets us simulate the function and verify, in this case, a robot project or a robot in software, and lets us see how logic works in the simulator before we have time to run it or before we run it on a physical robot. So again, for programmers, this is highly valuable knowledge, and we'll be doing this on Thursday night. So again, thank you for joining. Hopefully you got something from this, and I will be sending out a copy of the presentation or the video when we're all done.